Now you will learn about merge sort, which is a sorting algorithm that is much more efficient than bubble sort, selection sort, and insertion sort in runtime. The way merge sort works is by splitting the array into two smaller arrays of roughly equal size, then sorting each of them, then merging them together afterward. So in this example, it splits this array of length 9 into an array of length 5 and an array of length 4. Then it sorts each of these, so 2, 3, 4, 4, 7, and then 0, 1, 6, 9, and then it merges these two arrays. The way the two arrays are merged is that two indices are kept track of the entire time, initially put at the first element of each array, so in this case 2 and 0. Then afterward, I put the smaller element in the array. Then afterward, I advance my index. So now we're keeping track of 1 and 2 in this example, and 1 is still the smaller one. Now we're keeping track of 2 and 6 here. 2 is the smaller one. And now we're keeping track of 3 and 6 here. So 3 is the smaller one. And then we're keeping track of 4 and 6 afterward, and 4 is the smaller one. And similarly, we put 4 again. Then we're comparing 7 and 6. 6 is the smaller one. Then afterward, we compare 7 and 9. 7 is the smaller one. And then 9 is the only element left. So we put 9 in the array. And there's our resulted sorted array. Note that when we split our array into two halves and sort each half, we do it recursively. So basically, for this half, we also have to split it into two halves, which are 4, 7, 2 and 4, 3. Then recursively sort each of those, then put them back together. And similarly, in order to sort 4, 7, 2, you need to split it into 4, 7, and 2, and then merge them together after they're sorted, and so on, all the way up down to the single element. Let's go over this entire process manually to make you understand this better. So first, we split the array into two halves. Then afterward, we recursively merge sort each half. So we want to sort 4, 7, 2, 4, 3 first. So for that, we split it into two halves again. So 4, 7, 2 and 4, 3. And then afterward, we want to merge sort this 4, 7, 2 first. So basically, we split 4, 7, 2 into two subarrays, 4, 7, and 2. And then we want to merge sort 4 and 7, so we split that into two subarrays, so 4 and 7. Then afterward, 4 is already sorted, and so is 7, so we want to merge them in order to get 4, 7. Then afterward, we have our array 4, 7, and 2. And 2 only has one element, so we can just directly merge these to get 2, 4, 7. Then now we're done with 4, 7, 2. So now we want to sort 4, 3. So then for 4, 3, we split it into 4 and 3. And then afterward, since these each have one element, we can merge them to get 3, 4. Then afterward, we're done with 4, 7, 2 and we're done with 4, 3, so we're ready to merge them. So we currently have 2, 4, 7 and 3, 4 as our two halves. Then when we merge them, we get, first of all, 2 is the smaller of 2 and 3. So we put 2 here. Then now we're comparing 4 and 3. 3 is the smaller one. Then now we're comparing 4 and 4. 4 is the smaller one. Let's just say this 4, for example. Then we ran out of elements on this side, so automatically the remaining elements on this side get put into the array. So now we've sorted the left half of the entire array. Then for the right half, we did the exact same thing. We split 6, 9, 0, 1 into 6, 9, and 0, 1. Then again, we want to sort 6, 9, so we split that into 6 and 9. Then, since these each have one element, we merge them to get 6, 9. Similarly, when we sort 0, 1, we split that into 0 and 1. and when we merge them we get 0, 1. Then we're done with 6, 9, and 0, 1, so we're ready to merge them to get, well, first 0 is less than 6, so we put 0. Then 1 is also less than 6, so we put 1. Then we ran out of elements on this side, so now we put the elements of the other side into the array. So now we've sorted both halves of the array. Now all that's left is to merge the two halves. So we have 2, 3, 4, 4, 7, and 0, 1, 6, 9. So that when we merge them, 0 is less than 2, 1's less than 2, 2 is less than 6, 3 is less than 6, 4 is less than 6, 4 is less than 6, 6 is less than 7, 7's less than 9, and 9's the remaining element, and we've sorted the array. Let's implement merge sort in Java. So we'll need a method for this. We can't just do it in the main method because this is a recursive algorithm. So public static void merge sort, and of course we'll need an array and the window. And we need a window because we need it to do our recursion. When we split it into two halves, we just need to change our low and the high rather than generate a new array and pass it. So for this one, first, if low equals high, that literally means that the array is one element, or at least the window is one element, so we don't need to sort it, so we just return. Then afterward, we choose a mid, so mid equals low plus high over 2. Then we have to recursively merge sort the array with low and mid, and then merge sort the right half of the array with mid plus 1 and high. Then afterward, we're ready for the merging process. For the merging process, we'll need to keep track of two indices. Let's call them left index, set that one to low, and right index to mid plus 1, which low and mid plus 1 are the first elements of each half of the array. We'll also need a temporary array because if we modify ARR directly while we're reading it, then we'll lose information. And the size of temp should be high minus low plus 1, since that's how many elements there are from index low to index high of ARR. And we'll also need an index for where I insert the elements into temp. And note that left index is low while index is 0. That's because when we're dealing with ARR, we're dealing with indices from low to high. But when we're dealing with temp, we're dealing with indices from 0 to high minus low. And later we'll also need to adjust for that. And in the given example, we would have, before the sorting of the two halves, we would have that. Then after the sorting of the two halves, we would have 2, 3, 4, 4, 7, and 0, 1, 6, 9. And then left index would initially be 0, which is where 2 is in the array. Right index would be 5, which is here. And then index would be there. Now we'll need a loop. So let's do while index is less than temp.length, which is basically saying while there's still elements left to insert into temp, or equivalently, while there's still either something on the left side or something on the right side that I didn't have. Then we'll need to see whether we insert the element at left index or the element at right index. So in order to do that, we check if ARR of left index is less than ARR of right index. Then what we do is basically temp of index equals ARR of left index, because we want to insert the smaller one into temp earlier. Then left index plus plus. Then otherwise, temp of index equals ARR of right index, because we have the ARR of left index is greater than or equal to ARR of right index, and we want to insert the smaller one. and then afterward right index plus plus. And of course we need to increment index as well. So then in this example, we would first compare 2 and 0. We would find that 0 is smaller, so now we're at this else. So then temp of index, so let's say our temp is like this, an empty array with all zeros. And then temp of index, which is currently right here, equals ARR of right index, so we would put 0 there. Then we would increment right index like that. Then afterward, we would increment index. So now index is here, which means we're inserting, next element we insert is there. And now we repeat the process. So then we compare the elements at indices left index and right index. We still find that the one at right index is smaller in this case. So then we insert 1 right here, we increment right index, and we increment index. Then afterward we compare 2 and 6. 2 is smaller, which means now we're in this body. So then we first do temp of index equals ARR of left index, so we set that to be 2. We increment left index. And then afterward, we increment index. Then afterward, we're comparing 3 and 6. And again, 3 is smaller, so we increment left index. And then we increment index. Then again, 4 is smaller than 6, so then we increment, so we put 4 here, and then we increment left index. Then afterward, we increment index. Then afterward, 4 is also still less than 6, so we put 4 here, and then we increment left index, and we increment index. Then afterwards, 7 is greater than 6, so we put 6 here, and then we increment right index, and we increment index. Then afterwards, 7 is less than 9, so we put 7 here, we increment left index, and we increment index. Then afterward, here comes our problem. If we just used our code right here, then we're comparing the element at left index and the element at right index, and we would just insert 0 in this place, which is clearly not what we want. We want to insert 9. So what's wrong? Well, what's wrong is that we went to the right half of the array with left index. We've already used up all the elements on the left side, and now left index is on the right half, and we don't want to do that. So in other words, instead, what we want to do is just put the 9 instead of putting the 0. And the way we're going to do that is, well, check whether we ran out of elements on either side. So if we ran out of elements, so if left index is greater than mid, in this example mid is right here, then what we do is just insert it at the right. So temp of index equals ARR of right index plus plus. Then otherwise, if right index is greater than high, so if right index is like here, say, that's not good. That would cause an array index out of bounds exception. We don't want that either. So we just do temp of index equals ARR of left index, then left index plus plus. And by the way, we won't have both of these happening because by then index is no longer less than temp.length. And of course, we need to put the rest of these in the else, because we don't want to execute them if we ran out of elements on one side. We only execute these once we've made sure we haven't run out of elements on either side. Now, it may seem like we're done, but we're not yet done. All we've done is change temp. However, we need to change ARR for us to be finished, because that's what our sorting algorithm is supposed to do. Basically, make ARR sorted. So in order to do that, we just migrate the elements from temp into ARR. So we'll use a for loop, int I equals low, I is less than or equal to high, I plus plus. Then ARR of I equals temp of I minus low. And remember, this is because that when we're dealing with indices of temp, we're dealing with 0 through high minus low, but for ARR, we're dealing with low through high. So we need to deal with that offset by subtracting low from I when accessing the elements in temp. Then now we're done. So then when we run our algorithm on our sample array, we'll get that it's sorted after we print it. Now you'll see an advantage to using merge sort rather than bubble sort, selection sort, and insertion sort, which are all easier to program. So let's just say we have an array of length 500,000, and let's populate it. So huge ARR of I equals I. And now let's do bubble sort of huge array. If we put bubble sort, selection sort, and insertion sort down here. So when we run it, it seems to take a long time, and actually it will take a long time because as we went over, it takes quadratic time, and that can't handle 500,000. And similarly, selection sort won't work either. It'll take a long time because, well, the array is of length 500,000. And now, when we do insertion sort, it may appear to work as shown below. It takes almost no time. But as we went over, insertion sort takes not a lot of time if it's already sorted or nearly sorted. However, if we make it like not sorted at all, like in descending order, for example, then again, it'll take very long. Finally, if we perform merge sort on this array, and we do it from 0 up to, say, huge ARR dot length -1, then we run it, it takes almost no time. So merge sort is significantly more efficient than the other 3 sorting algorithms we've went over so far. The runtime of merge sort is n log n on average, and in the worst case. And one way to visualize why this is true is by looking at the following. So basically, all the time comes from the merging. So first we have to merge the individual elements. Then afterward we have to merge 2 elements at a time, and 4 elements at a time, and so on, until we have to merge the entire array together. And there's log n of these layers of recursion, so therefore overall it's n log n. N for every row, and there's a total of log n rows. In Java, fortunately, you don't have to implement merge sort or any other sorting algorithm by hand if you want to just sort an array. In order to sort an array in Java, you just have to do, so if we have an array, all you have to do is arrays.sort arr1 or whatever name you have for the array. And then when we print the array, it should be sorted. Arrays.sort uses something called quicksort to sort primitive data types, and we won't go over quicksort in this class, but it does use merge sort to sort objects, so like arrays of strings.